Welcome to lecture series on digital electronics under EPG Pathshala. In this module, we are going to learn about delay and hazards in combinational circuit, which is basically the last topic in combinational logic circuit design. So far, we have discussed several topics like logic gates, adder, subtractor, multiplexer, demultiplexer, encoder, decoder and so on. Even we have discussed the design process of all these blocks. In the previous session, we have discussed about how 1-bit LU can be designed, and the same concept can be extended further for n-bit LU design. But there is one important thing that we have to understand, that here we have assumed all these building blocks are ideal building blocks. But when we talk about in real life design situations, we know that every logic gate or building block has inherent delay, and this delay is because of the propagation kind of delay. Now, when we talk about the static behavior of any circuit, we encounter certain propagation delay. When we talk about the transient behavior or AC behavior, we always find out that there are certain glitches or transients which are appearing at the output. So, in both the cases, whether it is static or dynamic conditions, we have some kind of hazards, those are present in the combinational circuit. Now, we need to deal with some of these hazards. Hazards are classified into 3 different types, but when we talk about hazards, we need to understand what the hazard is. Hazard is basically some kind of unwanted signal which is appearing at the output because of either glitch or a delay or some kind of unwanted transient. Hazards are classified as static hazards, dynamic hazards and function hazards. In this module, we will be focusing on understanding how different hazards are generated in the combinational circuits. Then we will even discuss how to detect different hazards, those are present in the combinational circuit, and if possible, let us try to eliminate them. All the hazards may not be eliminated, but there are certain tricks or techniques we have to use so that we can eliminate some of these hazards. So, let us focus it on how do we get familiar with eliminating the hazards in the combinational circuit. Let us begin with the learning objectives of this module. The first one is to understand what delays, glitches and hazards are. Presence of unwanted signals give rise to various hazards. Next, let us study different types of hazards. The knowledge of steady state and dynamic behavior of the system can help to understand delays and hazards. For hazard free operation, it is essential to learn the techniques of detection and elimination of hazards. In combinational circuits, the output of the circuit is dependent on the present input combinations. This statement is true with the assumption that the circuit is built using ideal logic components. Ideal behavior assumes that there are no propagation delays in the logic gates and other building blocks. The fact is, any combinational circuit is no longer ideal and delays are always present. Delays in steady state and glitches in transient behavior generate hazards. Hazards are harmful to all logic circuits. The term hazards specifies the unwanted switching transient, false output or glitches which appear at the output of a circuit. Hazards in any system are an undesirable effect caused by either internal deficiency of the system or external disturbances. In combinational circuits, these transients or glitches are due to finite propagation delay of the components along the different paths within the network. The difference in propagation delays are corresponding to different signal paths results in hazards. The hazard can also be defined as the actual or potential malfunction of a logic circuit during transition between two input states when single variable changes. The term malfunction means any deviation from intended or standard response. When the changes in the input signal do not change the output signal due to some form of delay caused by logic building blocks like NOT, AND, OR gates, etc. This generates a malfunctioning in the performance of the circuit. This is, however, a temporary problem, and the logic will finally generate a desired function output. Even though the combinational logic system is generating a correct output, after some time it is essential that hazards be eliminated, as they can have an effect on the overall performance of the system. In the combinational circuits, hazards will produce an unwanted output value. If such combinational circuits are used as building blocks of bigger digital system like a synchronous sequential circuit, then it will produce a transition to the incorrect state table. The hazards result in the false output value when different paths from the input to output have different propagation delays. It is the deviation from the standard response. There are three types of hazards: static hazards, dynamic hazards, and function hazards. In static hazards, when one input variable changes, the output changes momentarily before stabilizing to the correct value. There are two types of static hazards: static 0 and static 1 hazard. Let us now discuss about static 0 hazard. A static 0 hazard takes place when the output momentarily goes to 1, that is high state, for a short duration when it should remain at a constant value 0, that is low. Let us look at now static 1 hazard. If the output is ideally supposed to be 1, that is high state, but due to difference in propagation delay, if it turns out to be 0, that is low state, for a short period of time, then the circuit is said to have static 1 hazard. Let us look at now dynamic hazard. In static hazard, the output changes only twice, 1 to 0 and 0 to 1, or 0 to 1 and back to 0. In dynamic hazards, there is a possibility of an output changing more than once as a result of single input change. When an output is supposed to change value from 0 to 1 or 1 to 0, this output may change 3 or more times. If this situation appears at the output, the circuit is said to have dynamic hazards. Let us now talk about function hazards, a hazard that can be caused in the output signal when more than one input signal is changed simultaneously is called a function hazard. A static hazard occurs when a single input variable change should cause no change in the output of combinational circuit, but a short glitch of the incorrect logic level occurs. Here the output changes momentarily when it should not. The static 0, a hazard, is also called as POS hazards, and static 1 hazard is also called as SOP hazards. A glitch is an undesired transition that occurs before the signal settles to its intended value. In other terms, glitch is an electric pulse of short duration that is usually the result of fault or design error in a digital circuit. The glitches are generated because of the propagation delays of the logic gates. Propagation delay is a time associated with any digital circuit and is the time between when an input to the circuit changes until that change propagates through the circuit and changes the output. Every logic gate has its own propagation delay and is dependent on the fabrication technology of the device. This figure indicates the propagation delay in the NOT gate. Static hazard in a logic network is a transient change of an output value which is supposed to remain fixed during transition between two input states differing in the value of only one variable. When the output is supposed to remain at static condition 0, but goes to logic 1 momentarily during the transition of the input states, then the hazard is called as static 0 hazard. On the other hand, if momentary 0 is likely to occur in the output when it is expected to remain in static condition 1, then the hazard is called as static 1 hazard. Let us consider a simple circuit to demonstrate the static 0 hazards. This circuit consists of an AND gate and a NOT gate. The input signal is applied directly to one of the inputs of AND gate and the other input of the AND gate is obtained through the inverter, that is NOT gate. As the NOT gate is present at one of the inputs of AND gate, the signal at the input is delayed by one NOT gate delay time. When the input signal is at logic 0, NOT gate output is at logic 1. Hence, the output is at logic 0. When the input changes the state from 0 to 1, then the output of AND gate produces a small glitch which goes high momentarily and return back to logic 0 after some delay. The duration of the glitch or small pulse is propagation delay, or it is also proportional to the delay of that NOT gate. A static hazard occurs when one or more combinational logic circuit input signal changes value and the final steady state of the output value remains the same. Let us now study the hazards in any combinational circuit in general. To demonstrate the hazards in general combinational circuit, let us consider the circuit as shown here. This circuit consists of 3 AND gates and a NOT gate along with their interconnections. This figure also indicates the waveforms at various points in the circuit and the glitch generated at the output. Let us assume A is equal to 0 and B is equal to 1. The output of two AND gates is G1 is equal to 0 and G2 is equal to 1. At time t is equal to t1, an input variable A changes its state from 0 to become 1. So, now both the inputs are at 1. The output of gate 1, that is G1, becomes high after a time delay equals to the propagation delay of AND gate 1. The output of gate 2, that is G2, goes low after a time delay which is equal to the sum of propagation delays of the inverter and AND gate 2. Hence, output of the final AND gate Y goes high for a short duration. After some time, the output turns back to logic 0 as expected. This short duration high pulse is unwanted and called as static 0 hazard. Let us consider a simple circuit to demonstrate the static 1 hazard. This circuit consists of an OR gate and a NOT gate. The input signal is applied directly to one of the inputs of the OR gate, and the other input of the OR gate is obtained through the inverter, that is NOT gate. As the NOT gate is present at one of the inputs of the OR gate, the signal at the input is delayed by one NOT gate delay time. When the input signal is at logic 1, NOT gate output is at logic 0. Hence, the output is at logic 1. When the input changes the state from 1 to 0, then output of OR gate produces a small glitch which goes momentarily 0, that is low. The duration of the glitch or small pulse is proportional to the delay of NOT gate, and then the output returns back to logic 1. A static hazard occurs when one or more combinational logic circuit input signals change value and the final steady state output value remains the same. Let us now study the hazards in any combinational circuit in general. To demonstrate the hazards in general combinational circuit, let us consider the circuit as shown here. The circuit consists of 3 AND gates, a NOT gate along with their interconnections. This figure also indicates the waveforms at various points in the circuit and the glitch generated at the output. Let us consider A is equal to 1, B is equal to 1 and C is equal to 1 as initial condition. The output of 2 AND gates is G1 is equal to 1 and G2 is equal to 0, which provides the final output Y as 1. At time t is equal to t1, an input variable B changes its state from 1 to become 0. Due to this change in the input condition, the gate output will also change. The G1 gate goes from 1 to 0 after finite propagation delay, and output of gate 2 G2 changes from 0 to 1 only after the propagation delay of NOT gate and AND gate delay. During this period, both G1 and G2 are at logic 0. Thus, the output Y goes to 0 momentarily. This short duration low pulse is unwanted and called as static 1 hazard. Here we have assumed the propagation delays of AND and NOT gate are almost similar. The output returns back to logic 1 later as expected. In dynamic hazards, there is a possibility of an output changing more than once as a result of a single input change. In a larger circuit, whenever there are different routes from inputs to output, then there is a possibility of dynamic hazards. When an output is supposed to change the value from 0 to 1 or 1 to 0, this output may change 3 or more times. If this situation appears at the output, the circuit is said to have dynamic hazards. When multiple glitches occur at the output from multi-level circuit because of changing inputs, the only reason for this could be existence of 3 or more asymmetric paths, that is delay wise, of that input to the output. In such a circuit, routes may have different delays. It is a potential dynamic hazard. Here, changing output values differ from expected output. For example, a logic circuit is expected to change from 1 to 0, but instead of it changes from 1 to 0 and then back to 1, finally switches to the correct value to 0. Dynamic hazards exist when there are multiple paths with different delays from the changing input to the changing output. Dynamic hazards do not occur in properly designed two-level and or and circuits. It should be noted that two-level and or and circuit is properly designed if a variable and its complements are never input to the same first level gate. In the logic circuit, when more than one input variable changes at the same time, non-solvable hazards occur. These non-solvable hazards are known as function hazards. Function hazards cannot be eliminated as the actual problem lies with the specification of Boolean function. The only way to avoid function hazards is to restrict the changing of input variables. Ensure that only one input changes at a given time. In reality, restrictions are not always possible. For example, consider a circuit with 3 inputs. One of the input is connected to the clock circuit, the other one is tied to 1 or 0 and the third one is connected to random noise source. In such a case, it is impossible to restrict the other inputs from changing. Thus, restricting the changing inputs to only one is not an effective solution. Hazards are unwanted switching transients that may appear at the output of a logic circuit because of different paths exhibit different propagation delays. The effect of seriousness of hazards is dependent on the devices or the systems which receive momentarily transient signals. In case of digital system, the presence of hazards can cause the system to malfunction. Hazards can occur in combinational circuit as a result of changes in the delays. It also appears in sequential circuits as well. To detect and eliminate the static hazards from logic circuit, following procedure is adopted. Step number 1, write the Boolean expression for the given circuit and convert it into SOP form, sum of product form. Step 2, prepare the K-map for the circuit. Step 3, adjacent ones or zeros if the circuit is in the POS form, not covered by the same prime implicant indicates a static hazard. Fourth, remove the hazards by adding a redundant prime implicants so that any two adjacent ones are covered by the same prime implicant. Step 5, write the Boolean expression and redraw the logic circuit. Let us consider an example to demonstrate how to eliminate hazards. The circuit consists of sum of product form of the Boolean expression as shown here. Step 1, let us write the Boolean expression for the given circuit and convert it into SOP form. Here, expansion is carried out so as to include all min terms. The expression is y is equal to AB OR with B complement C, that is also equal to, let us now incorporate the missing variable, that is C in the first term and A in the second term. So, we get y as AB in bracket C plus C bar bracket complete OR with B complement C in bracket A plus A complement. Expansion of the above terms gives y is equal to ABC OR with ABC bar plus A B bar C plus A bar B bar C. Step 2, prepare the K-map for the circuit. As we look at the expression, it is a Boolean expression of 3 variables. So, we need to prepare a K map of 3 variables and the product terms are mapped on the K map as shown here. 2 adjacent ones are identified which are responsible for static 1 hazard. Step number 3, these adjacent ones not covered by the same prime implicants indicate there is a possibility of static hazard. Remove the hazard by adding redundant prime implicants so that any 2 adjacent ones are covered by the same prime implicant. Group the 2 adjacent ones responsible for static 1 hazards into another pair. The new pair of ones is thus formed, it will eliminate the static 1 hazard. Step 5, realize the new hazard free circuit. From the K map, it is clear that this new pair gives rise to the product term A into C. This new redundant term is added into the Boolean expression. Thus, the new output for the output of the circuit after the formation of new pair is given as y is equal to A into B or with B complement C or with AC, where AC is the new term. This new term will definitely provide a hazard free circuit. Let us now summarize the things that we have studied in this module. This module is focusing on delays and hazards in combinational circuit. We have seen that whenever we are designing any combinational circuit, it is necessary to understand if there is any effect of time varying signals or any static signals those are present. When we talk about any combinational circuit, these combinational circuits are no longer ideal combinational circuit. If there are signals appearing through different gates at the input of the combinational circuit, definitely there is a possibility of certain delay, and this delay is the propagation delay present in almost all combinational circuits. Now, whenever we are designing the combinational circuit, we need to look at the realistic picture, wherein there are 3 different types of hazards those are possible. We have seen that the first simplest hazard is the static hazard, and there are 2 types of static hazards, static 0 and static 1 hazard. In static 0 hazard, the input goes momentarily to high state and normally it should be 0. So, whenever it goes temporarily at high state, it generates some kind of a glitch. We call this as the static 0 hazard. Similarly, in case of static 1 hazard, the output is expected to be at high state, but it goes low temporarily or momentarily for certain duration, which is proportional to the propagation delay of the logic gate, and then it will come back after some time to the desired state. So, in both the cases, these are the unwanted propagation delays which are affecting the performance of the circuit. Now, the solution on the static hazards is to use some kind of 2 level logic gates, either AND or AND circuits. In addition to that, there are dynamic hazards those are present, wherein the input to output transitions, whenever we are talking about, will have certain number of changes at the output. If the output changes more than once, say we have listed that if the input changes 3 times, then naturally the output will go momentarily 3 times to the unwanted state and comes back to the normal value. In static or dynamic hazard, there is an important part, that is the propagation delay. Similarly, there is a third hazard that is present, that is a function hazard. This function hazard is the hazard wherein there are more than one inputs which are changing with respect to time. These are usually non-solvable hazards. The best way to avoid this function hazard is not to allow the inputs to change more than one. So, but in real situation it is impossible. So, function hazards are really difficult to eliminate, but static and dynamic hazards can be eliminated or detected and then eliminated by using some special technique. We have discussed the procedure for eliminating the static and dynamic hazards, wherein we have added certain redundant terms such a way that it will compensate for the delay. This is the way we can eliminate the hazard. Thank you.